Welcome! In this session, we'll explore problem number 509, the Fibonacci number problem. This is a classic question that's as much about understanding recursion in dynamic programming as it is about optimizing for time and space efficiency. Let's dive in and see how we can solve it using different approaches. The Fibonacci sequence is a series of numbers where each term is the sum of the two preceding terms, starting with the base cases f(0) equals 0 and f(1) equals 1. For any number n greater than 1, the formula fn equals fn1 plus fn2 is used to calculate the nth term. This means that if you know the two previous Fibonacci numbers, you can compute the next one in the sequence. Your task is to write a function that takes an integer n as input and returns the nth Fibonacci number. The input will always be between 0 and 30, inclusive, and the result will be an integer. The goal is to compute this efficiently for any valid n within the given constraints. To better understand the problem, let's look at some examples. If the input n is 2, we need to calculate f(2). According to the formula, f(2) equals f(1) plus f(0). Since f(1) is 1 and f(0) is 0, adding them gives us 1. So, the output for this input is 1. Another example is when n equals 3. Here, f(3) is calculated as f(2) plus f(1). From the previous calculation, we know f(2) is 1 and f(1) is also 1. Adding these results gives 2, which is the output for n equals 3. Building on this, let's consider the case where n equals 4. Using the same formula, f(4) is determined as f(3) plus f(2). From the earlier examples, we know that f(3) is 2 and f(2) is 1. When we add these two values together, the result is 3. Therefore, the output for n equals 4 is 3. The constraints for this problem ensure that n will always be between 0 and 30, and the result will fit within the range of a 32-bit signed integer. This means you don't need to worry about overflow or invalid input values. Efficient computation is key, especially for the larger values of n within this range. Let's consider edge cases to ensure the solution handles all situations correctly. For the smallest input, when n equals 0, the output is straightforward, f(0) is defined as 0. When n equals 1, the output is 1, since f(1) is defined as 1. For larger values, such as n equals 30, the solution must compute the result efficiently within the time limits. This means you'll need to avoid redundant calculations or excessive memory usage. Designing an approach that balances clarity and performance will help ensure your implementation works for all valid input values. To solve the Fibonacci number problem, we can explore several approaches, each with its own advantages and trade-offs. The first method is the recursive approach, which directly mirrors the mathematical definition of the Fibonacci sequence. The function simply calls itself recursively to compute the sum of the two preceding numbers. While this approach is intuitive and elegant, it has exponential time complexity, specifically O(2 to the power of n), because the same Fibonacci numbers are recalculated multiple times. Additionally, the space complexity is O(n) due to the function call stack. This makes the recursive method inefficient for larger inputs. To address this inefficiency, we can turn to a more optimized approach, known as memoization. Here, we store the results of previously calculated Fibonacci numbers in a dictionary or similar data structure. This avoids redundant calculations, significantly improving efficiency. With memoization, the time complexity is reduced to O(n), and the space complexity remains O(n), due to the storage requirements of the memoization table. This method is far more practical for larger inputs, although it does require additional memory to store the intermediate results. Building on the idea of optimizing performance, we have the iterative dynamic programming approach. Instead of using recursion or additional memory for storing intermediate results, this method starts with the base cases, f(0) and f(1), and iteratively computes the sequence up to fn, using a simple loop. By only maintaining the last two Fibonacci numbers at any given time, we reduce the space complexity to O(1), while the time complexity remains O(n) due to the single loop. This approach optimizes both time and space efficiency, making it the most practical solution for this problem. The trade-off here is minimal, we sacrifice the elegance of recursion for a more straightforward and efficient implementation. This makes the iterative dynamic programming method a very attractive choice, especially when working within the typical constraints of competitive programming or real-world applications. For more advanced scenarios, we can consider matrix exponentiation. The Fibonacci sequence can be expressed as a matrix multiplication problem, which allows us to compute f(n) using matrix exponentiation. This method has a time complexity of O log n, as the matrix is exponentiated using repeated squaring. However, the space complexity is also O log n, due to the recursion involved in the exponentiation process. While this approach is faster for very large values of n, it is more complex to implement and might be overkill for typical constraints. Another advanced method is Binet's formula, which provides a closed-form solution using the golden ratio. This method is incredibly fast, with O(1) time and space complexity, but it is prone to floating-point precision errors for larger inputs. Both of these approaches showcase the mathematical depth of the Fibonacci sequence but are less practical for everyday use due to their complexity or reliability issues. Ultimately, the iterative dynamic programming approach is the most practical choice for solving the Fibonacci number problem. It leverages the key observation that each Fibonacci number depends only on the last two values, allowing us to save space by using just two variables. This realization, or the aha moment, enables us to achieve both time and space efficiency, with time complexity of O(n) and space complexity of O(1). While matrix exponentiation is faster for extremely large values of n, it is less intuitive and more complex to implement. For most real-world scenarios and problem constraints, the iterative approach strikes the perfect balance between simplicity, readability, and performance. This makes it the ideal solution for the Fibonacci number problem, ensuring that it is not only efficient but also straightforward to debug and maintain. To solve the Fibonacci number problem, we need to calculate the nth Fibonacci number, which is defined by the sequence where f(0) equals 0, f(1) equals 1, and for any n greater than or equal to 2, f(n) is the sum of the two preceding numbers, fn1 and fn2. While there are several ways to compute Fibonacci numbers, we will focus on the iterative approach. This method is both efficient and avoids the pitfalls of recursion, such as stack overflow or redundant calculations. The iterative solution achieves a time complexity of O(n) and uses only O(1) space, making it an optimal choice for this problem. The first step in the algorithm is to initialize the base cases. We define two variables, previous 2 and previous 1, to store the two most recent Fibonacci numbers. Initially, we set previous 2 to 0, representing f(0), and previous 1 to 1, representing f(1). Next, we handle edge cases. If the input n is 0, we simply return previous 2, since f(0) equals 0. Similarly, if n is 1, we return previous 1, since f(1) equals 1. For values of n greater than 1, we proceed to iterate through the sequence. Starting from I equal to 2 and going up to n, we compute each Fibonacci number as the sum of previous 1 and previous 2. After calculating the current Fibonacci number, we update previous 2 to the value of previous 1 and previous 1 to the current value, effectively moving the window forward. Once the loop completes, we have iteratively calculated all the Fibonacci numbers up to fn. At this point, the variable previous 1 contains the value of fn, which we return as the result. There are several key insights to note about this approach. First, it is highly space efficient. Unlike recursive methods or dynamic programming that store all intermediate Fibonacci numbers in an array, this algorithm uses only two variables, previous 2 and previous 1, to store the last two computed values. This optimization reduces the space complexity to O(1). Additionally, the iterative approach avoids the redundancy inherent in recursion, where the same Fibonacci numbers are recalculated multiple times. This ensures a linear time complexity of O(n). By explicitly handling edge cases for n equals 0 and n equals 1, the algorithm also guarantees correctness for small inputs without unnecessary computation. When comparing the iterative and recursive approaches, an important distinction is that recursion can lead to stack overflow for large values of n due to the depth of recursive calls. The iterative approach avoids this entirely by relying on a simple loop and scalar variables. Speaking of variables, this algorithm does not require any additional data structures. We use just two scalar variables, previous 2 and previous 1, to track the most recent Fibonacci numbers. This suffices because every Fibonacci number depends only on the two preceding values. While it is possible to use an array to store all Fibonacci numbers up to n, doing so would increase the space complexity to O(n). By using scalar variables instead, we achieve the desired O(1) space efficiency. Let's look at an example to compute f(5) using the iterative approach. Initially, we set previous 2 to 0 and previous 1 to 1. We then start the loop. For I equals 2, we calculate current as the sum of previous 1 and previous 2, which is 1 plus 0, giving 1. We update previous 2 to 1 and previous 1 to 1. For I equals 3, current is again the sum of previous 1 and previous 2, which is 1 plus 1, resulting in 2. Updating, previous 2 becomes 1 and previous 1 becomes 2. For I equals 4, current is 2 plus 1, giving 3, and we update previous 2 to 2 and previous 1 to 3. Finally, for I equals 5, current is 3 plus 2, resulting in 5. After the loop, previous 1 holds the value 5, which is f(5), and that is returned as the result. Let's analyze the complexity of this algorithm. First, the time complexity is O(n). This is because we compute each Fibonacci number from f(2) to fn exactly once, and each iteration involves a constant amount of work. In terms of space complexity, the algorithm is highly efficient, using only O(1) additional space. This is due to the use of two scalar variables, previous 2 and previous 1, to store intermediate results, regardless of the input size. This combination of linear time complexity and constant space complexity makes the iterative approach an optimal solution for calculating Fibonacci numbers. This Python code solves LeetCode problem number 509, Fibonacci number, using an iterative approach. The goal is to compute the nth Fibonacci number efficiently using O(n) time and O(1) space. The solution is implemented within a class solution and its method fib_n. The function takes an integer n as input, representing the position in the Fibonacci sequence. The sequence starts with f(0) equals 0 and f(1) equals 1, and subsequent numbers are calculated as fn equals fn1 plus fn2. ### line by line explanation. 1. Base cases. The method first checks if n is 0 or 1. These are the base cases of the Fibonacci sequence, and the function directly returns 0 or 1 as appropriate. 2. Variable initialization. If n is greater than 1, we initialize two variables. Previous 2 to store fn2, starting from 0. Previous 1 to store fn1, starting from 1. These variables represent the two most recent Fibonacci numbers needed to compute the next one. 3. Iterative calculation. We use a for loop to compute the Fibonacci numbers iteratively, starting from f(2) and going up to fn. In each iteration, current is calculated as the sum of previous 1 and previous 2. Previous 2 is updated to previous 1, and previous 1 is updated to current, effectively shifting the two variables forward in the sequence. 4. Return result. After the loop completes, previous 1 holds the value of fn, which is returned as the result. ### key advantages. Efficiency. The iterative approach avoids the exponential time complexity of recursion and the extra space required for memoization. Space optimization. Only two variables, previous 1 and previous 2, are used, leading to O(1) space complexity. This solution is optimized for performance and simplicity, making it suitable for large inputs up to the problem's constraints, e.g., n less than or equal to 30. This is the Java implementation of the Fibonacci number problem, number 509, from LeetCode. The logic mirrors the Python solution, employing an iterative approach to compute Fibonacci numbers efficiently using constant space. Key differences include the use of explicit type declarations for variables and the class-based structure inherent to Java. The solution initializes two variables to track the previous two Fibonacci numbers, iteratively updates them, and finally returns the nth Fibonacci number. To begin, let's look at the simplest case where the input is n equals 0. When the function fib is called with this input, the first condition in our code, if n equals 0, is evaluated. Since this condition is true, the function immediately returns 0. There are no further calculations or iterations needed because n equals 0 directly corresponds to the base case of the Fibonacci sequence. Therefore, the Fibonacci number for n equals 0 is 0. Now, we move on to the next simplest case, when the input is n equals 1. Here, the function fib is called with n equals 1. Inside the function, the second condition, if n equals 1, is evaluated. Since n is indeed 1, this condition is true, and the function directly returns 1. Again, no additional steps or iterations are required because n equals 1 is another base case of the Fibonacci sequence. Thus, the Fibonacci number for n equals 1 is 1. Next, we explore a slightly more complex example where the input is n equals 5. When the function fib is called with n equals 5, the base case is if n equals 0 and if n equals 1 are both false, so we proceed to calculate the Fibonacci number iteratively. To start, we initialize two variables, previous 2 equals 0, which represents f, n2, and previous 1 equals 1, which represents f, n1. We then use a for loop to iterate from 2 to 5. In the first iteration, or step 2, we calculate current as the sum of previous 1 and previous 2, which gives 1. We then update previous 2 to previous 1, so previous 2 becomes 1, and update previous 1 to current, so previous 1 also becomes 1. In the second iteration, or step 3, we compute current as 1 plus 1 equals 2, update previous 2 to 1, and set previous 1 to 2. In the third iteration, or step 4, current is 2 plus 1 equals 3, and the values of previous 2 and previous 1 are updated accordingly. Lastly, in step 5, we calculate current as 3 plus 2 equals 5, making previous 2 equal to 3 and previous 1 equal to 5. After completing all iterations of the loop, the final value stored in previous 1 is 5, which represents the Fibonacci number for n equals 5. This iterative approach efficiently computes the result by reusing previously calculated values rather than using recursion. Now, let's consider the case where the input is n equals 10. For this input, we follow a similar iterative process to compute the result. For the input n equals 10, the base case is if n equals 0 and if n equals 1 are both false, so we proceed with the iterative computation. We initialize previous 2 equals 0 and previous 1 equals 1 as before, and then we loop from 2 to 10. During each iteration, we calculate current as the sum of previous 1 and previous 2, and then update previous 2 and previous 1 to hold the previous 2 Fibonacci values. For example, in the first iteration, current is 1, and the updates make previous 2 equals 1 and previous 1 equals 1. Similarly, in subsequent iterations, we calculate values like 2, 3, 5, and so on, until the ninth iteration where current equals 55. At the end of the loop, previous 1 holds the value 55, which is the Fibonacci number for n equals 10. This demonstrates how the iterative approach scales efficiently for larger values of n. When analyzing the time complexity of this solution, we see that it's O(n). This is because the algorithm uses a for loop that starts at index 2 and runs up to n, inclusive. For each iteration, the loop performs a constant amount of work, which includes one addition operation and two variable assignments. Specifically, it updates the values of previous 1, previous 2, and computes the next Fibonacci number, all in constant time. Now, if we denote the number of iterations as k, where k equals n1, the total time taken by the loop becomes proportional to k, and since k is directly tied to n, the overall complexity simplifies to O(n). This holds true for the best, average, and worst cases because the number of iterations solely depends on the input value n, and the work done in each iteration remains constant. Let's now explore the space complexity of this solution, which is O(1). The algorithm is optimized to use only three variables, previous 2, previous 1, and current, to compute and track the Fibonacci sequence. These three variables are sufficient for the computation, and no additional data structures, such as arrays or recursion stacks, are needed. Because the number of variables remains constant, regardless of the size of the input n, the memory usage does not grow with the input. This means the space complexity is constant, or O(1). Whether the input is small or large, the memory footprint of the algorithm stays the same, making it highly efficient in terms of space usage across all cases. To put this solution in context, let's compare it with other approaches. A naive recursive solution computes Fibonacci numbers using repeated recursive calls, which results in a time complexity of O(2 to the power of n) due to overlapping subproblems and redundant computations. Additionally, the recursion stack depth grows linearly with n, leading to a space complexity of O(n). On the other hand, a dynamic programming approach that uses an array to store Fibonacci numbers has a time complexity of O(n), similar to our solution, but its space complexity is O(n) because of the array storage. In contrast, the current iterative approach combines the best aspects of efficiency. It achieves a time complexity of O(n), like the dynamic programming approach, but with a superior space complexity of O(1), since it uses only 3 variables. This is because each Fibonacci number is computed using only the last 2 numbers, and no additional memory is required. The linear nature of the algorithm and its constant memory overhead make it an optimal solution for this problem. When working with Fibonacci problems, there are several common mistakes that can trip you up. First, using plain recursion without memoization is a major pitfall. This approach recalculates the same Fibonacci numbers over and over, leading to exponential time complexity, or O(2 to the power of n). This becomes highly inefficient as the input size grows. To fix this, you can use memoization to store previously computed values or switch to an iterative approach for better performance. Another issue arises from incorrect base cases in recursion. If you forget to define base cases like Fibonacci 0 equals 0 and Fibonacci 1 equals 1, your function might enter infinite recursion or produce incorrect results. Always make sure to define and test these base cases first. A third challenge is stack overflow when using recursion for large inputs. Without tail call optimization, deep recursion can cause the stack to run out of space. To address this, iterative or dynamic programming approaches are safer alternatives. Lastly, dynamic programming tables can lead to space inefficiency. Allocating an entire array for Fibonacci numbers up to n is unnecessary when only the last 2 values are required. A bottom-up approach that stores just these 2 values can drastically reduce space usage while maintaining correct results. Now, let's talk about additional challenges and insights. For instance, integer overflow can occur in languages with fixed integer limits. As Fibonacci numbers grow quickly, results might exceed the maximum value of an integer type, leading to incorrect outputs. The solution here is to use data types that support larger numbers, like long in Java, bigint in Python, or libraries like biginteger in Java. In interviews, you might also encounter variations involving modular arithmetic. For example, you could be asked to return the Fibonacci number modulo some value, like 10⁻9 plus 7. Implementing modular arithmetic correctly not only avoids overflow but also ensures the solution is efficient. Being able to analyze time complexity is another key interview skill. You should be ready to explain how efficiency improves across different approaches, from the naive recursive O(2 to the power of n, to memoized O(n), iterative O(n), and even matrix exponentiation at O log n. It's also important to recognize patterns similar to Fibonacci in other problems. Many recurrence relations share the same structure, and identifying these connections can help simplify complex problems. Lastly, testing edge cases is critical. Small inputs like n equals 0 or n equals 1 validate correctness, while large inputs, often exceeding 10⁻5, ensure scalability. Fibonacci-like problems appear frequently in coding challenges, so practicing related problems can deepen your understanding. For example, the climbing stairs problem on LeetCode, problem 70, follows the same recurrence relation as Fibonacci, where each step builds on the previous 2. Similarly, the house robber problem, LeetCode 198, demonstrates the power of dynamic programming with overlapping subproblems, a concept closely tied to Fibonacci logic. Another example is unique paths, LeetCode 62, which involves recurrence relations and combinatorics. Understanding its connection to Fibonacci can help solve it more intuitively. Lastly, the minimum cost climbing stairs problem, LeetCode 746, builds directly on Fibonacci-like logic, but instead of summing values, you compute the minimum cost to reach the top. These problems highlight how versatile the Fibonacci sequence is and how mastering it can unlock solutions to a wide range of challenges. When solving Fibonacci problems, several alternative approaches are worth considering, each with its own trade-offs. A recursive solution with memoization is a good starting point. It reduces the time complexity to O(n) by storing intermediate results, but it comes with an O(n) space cost due to the memoization table. Alternatively, the iterative approach achieves the same O(n) time complexity but requires only O(1) space, making it more space efficient. However, some might find it less elegant than recursion. For advanced scenarios, matrix exponentiation is a powerful technique that reduces time complexity to O log n. This approach relies on the mathematical properties of matrices but can be harder to implement and less intuitive, especially for beginners. Finally, there's Binet's formula, which provides a direct computation of Fibonacci numbers using the golden ratio. While it's mathematically interesting, it's prone to floating point precision errors for large values of n, making it less reliable in practice. Understanding these approaches and their trade-offs will help you choose the best solution for the problem at hand. Great job! Today, we tackled the Fibonacci number problem and explored different ways to optimize it. Remember, practicing problems like this will deepen your understanding of recursion and dynamic programming. Thank you for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!